Alright, good evening, students. Once again, welcome to CTS physics class. Um, before class start, before we start our next topic, which is atomic structure and radioactivity, we'll be doing the homework from last week, which was given for both CXC and IGC. All right. So we'll start firstly with the IGC past paper, which was given as pages 16 and 17. And the question is as follows for everyone who here should be able to see the shared screen. Good. So this is the IGC question, and it goes as a figure 9.1 shows a simple electric motor with a single rectangular coil between magnetic poles X and Y. So we don't know which is this, if it's north or south or south or north. We are asking now in the question, add labels to the empty boxes to the right of figure 9.1 to identify the parts. Which is this here? Which on the chat, anybody do it? Which is this one here? Anybody do it? So this one here should be something called a commutator, because we would have done this last week, which would have been last week Friday. And I said that this was similar to the past paper question that we did in CSEC. Good, so this is your commutator part. This one here, this black thing here, what we call this? If we go back to the notes, you will see the notes here. This is your commutator, this half a circle, and next to it is this black little gray thing here, which is your brushes. Your answer for that is brushes. Alright? Did everyone get that so far? Well, IGC students in particular. Everyone get it? Right, nice. So we're moving on. So those are the two that identified. Let's go back. The first one is the commutator. That's the half a circle thing, and your brush is black rectangular that is connected to it. Good. As later down now, the coil rotates in a clockwise direction when viewed from point P. So this is point P, so it's going a clockwise direction. So that means at this point here, it goes up. So here, since it is a small pole, your small pole is always a negative. So this is your negative, your big pole is your positive. Alright? So that means current will be flowing in here in this direction. Good. Um, so yes, it will be flowing in this direction. Wow. Alright, in this direction going in. Good. And I'm going straight into this one, so current going to be flowing here too as well. Good, and then I'm going to be flowing to go back to the negative point, which is here's what I want. So alright, so you're going to be going back in this direction here to the negative. So if it is coming in this direction here and the rotation is up, if we draw in it from the shade screen, again, if this is an electric motor, which law we use? Fleming's right hand or left hand? We go back to the notes. For motors, you would be using Fleming's Left hand rule. Good? Nice. So Fleming's left hand rule is what we're using. So if it is the left hand rule, here, we go to the shade screen. So your left hand rule is as follows. So your current flowing in this direction. So if here is current, your field is this direction and your motion is in direction. So this is where it going to the motion. This is motion or movement, and this is your field. If your field pointing in this direction, then here going to be north in going into this direction. So this side of the pole going to be north, and this side going to be south because your magnetic field is pointed in direction. So if we go back to this here, so you have this direction coming in here. So between X to Y, your magnetic field is going to be in this direction between X to Y. So they're asking the question, state which of the magnetic pole X or Y is the north pole. So your north pole going to be your X here because it's going to be pointing from, if you go back to the shade screen, from this direction here, in this direction. Good? Yeah, going from north to south. That's if you put your finger. So if you directing your finger, your middle finger should be pointing in the direction of the direction of this V. Your your forefinger should be pointing in the direction of the X and Y. X going towards Y, and your thumb should be pointing in upward direction as shows in the P. Good? Everybody understand that so far? Everybody okay with that so far? How we get X? Good. So all right. So let me go back here. The question asks, the coil rotates in a clockwise direction when viewed from point P. So this is a clockwise direction. That means this point going to be moving upwards. Good. And then this one going to be moving downwards, which are going a clockwise direction. Good. So for this to go upwards and your direction to be coming outward, using Fleming's left hand rule. And in your left hand rule, point the thumb to face upward as in the direction of P. Put it towards the computer and face the thumb upwards as in the direction of P. The forefinger goes from X to Y and the middle finger shows in the direction of your current flow. So the middle finger should be coming out of the computer screen facing towards you. Your forefinger gives you the direction of the poles where it goes to north pole. So you're starting from X, so X goes to north to south because your magnetic field always goes from north to south. Good. So your north pole would be X and your south pole would be by Y, so that it could be pointing in that direction. The magnetic field could be going in that direction. All right, so that's how we get the north pole being X. So are you okay with that so far? Did we good with that? Good, nice. So we're moving on. This is right, good. So they said suggest two changes that could cause the motor to spin faster. So if we go back to our notes, what could cause a motor to spin faster? Factors to increase the speed of a turning effect, which is the same thing as a motor. What we could do, increase the current, use a stronger magnet, or increase the number of turns in the coil, or the increase the area of the coil. So we have four things, but they only ask us for two. So we could say we could increase the number of increase the number of coil, increase the number of turns on the coil, sorry, increase the number of turns on the coil, and the second one we could put is increase increase the strength of the magnetic field, or the magnet, right? In this case, it's going to be magnetic. The magnet, sorry. Good, sir. Everybody okay with that so far? Hence the reason we use coils in our magnets. We no longer use permanent magnet, because if you want a stronger motor or motor to move faster, the easiest thing to do is to use coils rather than a magnet. The bigger the permanent magnet, in order to get stronger magnetic field, you would need a bigger magnet. And the bigger the magnet, the heavier the motor. So to prevent that, we use electromagnetic coils in the motor itself. All right. So everybody okay with the answers so far, IGC students? Good. Here we go. They say state the effect on the motor of reversing the connection of the battery. So think about it. This is how we connect. This is the simplest motor we have. This is something called a permanent magnet. You can write down that permanent magnet DC motor. This is a permanent magnet DC motor. It is the same motor that you have in your toy cars. Normally, most of them would have by remote control cars, and you can take out the motor and play with it after a while when you get fed up. All right. The connection are like this here. If you reverse the connection, what you think going to happen to the rotation? Right now it is clockwise. So you connect the red wire to the negative terminal, the black wire to the positive terminal. However, I switch it wrong. What do you think going to happen to the motor? Hmm? It will go anti-clockwise, exactly. It will rotate. It will rotate in an anti-clockwise direction. Good. So only for these type of motors, this permanent magnet DC motor, you could reverse the connection, like switch on the battery connections for it to go in the reverse direction. However, any other motor, you would have to reverse the field connections and so forth. Good. But at this stage, you're only doing permanent magnet motors, so your answer always going to be reverse reverse the connection in the battery to reverse the direction. Good. So moving on. They said now the battery in figure 9.1 is replaced with a resistor. So simple. All they do, they add a resistor to it here, like here. They just connect a resistor to it. They are saying the coil is made to rotate by an external mechanism. So it's no longer a motor. What they do here, they connect a handle here and they put a resistor. So when you turn this, it becomes a generator. They are asking you now, explain why there's a current in the resistor. Why does it have a current? Hmm? If we go back to our notes in the generator, um, here. First off, electromagnetic. And if a conductor is placed in the region of a changing magnetic field, an EMF will be induced in it. Good. So, which is exactly what we mean by electromagnetic induction? The production of an EMF in a conductor due to a change in magnetic field. So, your answer here should be explain why there is a current in the resistor due to the um explain why there's a current resistor. Good. So basically, they're asking here. They said the battery in 9.1 is replaced with a resistor. The coil is made to rotate by an external mechanism. So you're gonna turn the coil now, right? Think about a handle and you're turning it. Similar to this here, our notes that was given when we did generators here. So you're gonna rotate this here. Good. When you rotate this, you're going to cause a current to flow because you're cutting the magnetic field, right? And because of that, this is due to the production of an induced EMF that is created when a conductor is placed in a changing magnetic field of flux. Good. Everybody okay with this answer? This is basically electromagnetic induction, the definition. So you are going to write definition for this one here. All right. Are you okay with this so far? IGC students. Yeah, good. Nice. So we're moving on. So it was 8 marks. We're moving on now to this question here. Figure 10.1 shows a coil of wire rotating steadily in a magnetic field between the poles of a permanent magnet, similar to what we just do. The current generated in the coil is passed through a resistor R. The apparatus in figure 10.1 is part of an AC generator that is connected between ends A. The apparatus in figure 10.1 is part of an AC generator. What is connected between ends A and B of the coil and the connection C and D? So what do you think here? You're going to have, if you go back to AC generator, with the notes, right? In our notes. Yeah, this is a AC generator. So between the terminals here, what we have here, we have something called slip rings. Good. So they're asking what it is that is placed between here. It's slip rings between the 2 points. Or commutators. If it was a DC generator, it would have had commutator. Good. So we're going back to the notes, the past papers here, which is they said the apparatus in figure 10.1 is part of a DC jet an AC generator. What is connected between the ends A and B of the coil and the connection C and D? Your answer for this would be slip rings and brushes. Good. The brushes is the block that is always connected to the slip rings. Remember it's slip rings because why is an AC generator. Once it's AC generator, you have slip rings, and DC generator, you have commutators. DC generator, you have commutators. Good. Once a DC is commutator, AC is slip rings. Everybody okay with that so far? IGC students, nice. So good. So you could practice the other questions that it have any past papers here. Um, you could try this. This is simple because this is the answers that were given over here. These are your slip rings and brushes here, and this is the output voltage. Explain why rotating the coil produces an output voltage. Why is because the conductor was placed in the because a current conductor was placed in the changing magnetic field. Good. All the answers going to be around the same thing, so you could practice the other two that it have. Then, so see IGC students, you're okay with that? Everybody okay with that? IGC. Nice. So we're moving on to CXC now. For the CXC students, right? Question here. The question here says, an experiment in which a magnet was allowed to fall through a coil was conducted to test the concept of induced EMF. The voltages was recorded at different time intervals. Good. So here they give you everything: time, EMF. They had also given you the scale. They say a scale of 2 centimeter to 5 centimeter, 5 millimeter per second on a horizontal axis, 2 to 5 volts on the vertical axis. So voltage on your Y and time on your X. Good. So just going in. Good. So you would have a drawing like this here, where you have time, you have voltage, and if voltage is in volts, your time is in milliseconds. Good. And you're going to draw it out. They give you the scale. Your scale obviously is 2 centimeter to whatever. I had posted on the group chat for you all. Most of you all would have seen the group chat on WhatsApp. Let me just pull it up so you can get to see the answer. The CXC students, you could go to the group chat and you would see it. Good. So you go see on the shared screen. You should see the graph and plot out. Everybody seen this? CXC students in particular. You all seen the graph here? Good, nice. So the graph, the question was given where you had to plot these points. It was not a straight line graph. However, you were to plot this graph here. They had indicated. So your graph looks like this here. Um, where you would have a waveform. They had asked you here in the past paper question. They said, from use your graph. I would assume that everybody would have drawn a graph since it was homework. If not, there for you to see. They said use your graph to determine the induced EMF after 12.5 milliseconds. So we're going back to your graph here, which was drawn 12.5 milliseconds. So it's average about here. You go straight upward and you go across. It should be around, I have around 1.25 millivolts. So my answer I'd gotten here was around 1.25. Wait, the induced EMF after 12.5 milliseconds. We just go back just to make sure. Good. So here, so after 12.5 milliseconds, so here's 15 between here to here, so half of it will be 12.5. So we're going up here at this point to touch here and go across, so it's around, sorry, I get 15, my mistake. Around 15, sorry, 1.5 volts. Yeah, 1.5, nice. I got 1.5, I make a mistake. Alright, so 1.5 volts, zero point 0.5 volts. Good. Moving on. The time, so they ask you to in the graph to determine the time in milliseconds other than that at the beginning of the experiment when the induced voltage was 0 volts. So we're going back to the graph here. So when it was 0 volts, it was around here. So it could be around, let me just say average, my sketches graph. So it might be around 12, about 2.75 or 2.8 volts milliseconds, sorry. So around, you all got that around 2.75 or 2.8, 28, good, 28, sorry, not 2.5, I make a mistake, 25 or 28, yeah, 28 milliseconds. Good, so your answer is around 28 milliseconds. Sorry about that, yeah. So good. Lower down the question is that Kevin, a physics student, conducted an experiment to determine the effects of an electromagnetic induction. He used the following apparatus: a coil made of fine wires, a sensitive galvanometer, connecting wires, a bar magnet. The figure 1 shows the setup of the experiment used by Kevin. Coil of wire, of fine wire, and this is your galvanometer. They are asking here, they said the magnet is pushed into the coil. So here is a magnetic field between this point here. So I'm going to use the shade screen to draw better. Alright, so this is your magnet here, North Pole. So your magnetic field would be like this. Then you have this coil connected to a galvanometer, which means that some current, right, which means that some current. So if we go to use Lenz's law states that how we going to determine here. So let's go back now to the question. The question here says how the magnet is pushed into the coil with the North Pole entering first. Draw on figure 1 the direction of the induced current and the direction of the arrow on the galvanometer as a result of the motion. So let's going back to your notes so that you can see what the notes is about. Share. Here the notes say the direction of the induced EMF is always such as to oppose the change that produces it. Good. So that means that the production of the EMF, however you're going to produce it, the current going in the opposite direction so as to cause the EMF to be produced or the voltage to be produced. Good. Well, no whiteboard here. So your magnetic field is in direction here. Lenz's law, you're using your hand like a cuff. Think about the screw rule, your hand like a cuff for Lenz's law. You're pointing, you're pointing. So your hand's going to be like this. This is your thumb. But I have it the wrong side. Alright, so your thumb like this. So this is your thumb here. So your thumb in this direction. All your fingers are going to be pointing downward. So if you point the direction of the magnetic field like that, remember your north pole is going in this direction. So your magnetic field is in this direction here. So you have to flip your hand on the next side. So your hand would be like this. This this would be your fingers here. Good. So you're pointing the direction. So that means your current going to be going like this here. If you point it in that direction, your current going to be going where? Downward, right? So your current going to be going downward here. And it's going to be going upward. Okay, not the thumb, the nails of your fingers point in the direction of the current flow. So that means the current going to be going in a circular direction. So if current flows in here, shoot, right. If current flows in here, that means your galvanometer going to read which direction? To your left or to your right? This is your right here, and this is your left here. Which do you think you're going to be? To your right. Good. Right. So, alright. So you're going to be going in this direction here. Good. No, we go back to your notes to see, just to make sure. I want you to read this first before we continue. Just sharing back the screen with the notes. Right here it says when the bar magnet is pushed into and pulled out of the coil, the meter shows the current is induced in one direction and is moved it is in the opposite direction. So when you're pushing the bar magnet is deflected in the direction of the movement, which is one will be north and one will be south. So in this scenario here, um, you're going to be moving in this direction here, the right side. Yeah? Now let me go on to the next question. Everybody okay with that so far? Next question here says, explain why an induced current is produced. Why is because a conductor this is because a conductor no, the conductor was placed in a changing magnetic field. Good. All right, right, my mistake. Sorry. So the question here says, explain why an induced current is produced. The conductor was placed. Conductor was or is placed in a changing magnetic field. That's the reason you get the current is because of the interaction between the conductor and the changing magnetic field that causes it to produce a current. Explain why it is necessary to use a sensitive galvanometer because the induced EMF produce is very small because the induced EMF is very small. Why is it necessary to use a sensitive galvanometer? Because the induced EMF produced is very small. Right? Because the voltage is so small, you need to use a sensitive galvanometer. Otherwise, if you go to use a normal voltmeter, you wouldn't really see any big change because of the size of the the magnet and the is just a single loop. Alright, they said the magnet is then pulled out of the coil. Show in figure to the direction of the induced current. Yeah, so we use them at the same widescreen now. Just instead of going in direction, going in the opposite direction now. What do you think going to happen? The current obviously going to flow in the opposite direction, right? So that means your current going to be flowing like this. The deflection going to be like that. Good. Mm-hmm. So everybody okay with that so far? IGC students, you good with that? Nice. So they said now, lower down, state three changes or adjustments that Kevin could make in this experiment to increase the EMF. So if you go back to our notes here, how to increase the EMF, we have different ways to increase. To increase the induced EMF or induced voltage, we could do three things. Increase the speed of the motion of the magnet or coil. So the first one would be to increase state three changes. One, increase the speed of motion of the coil of the magnet or coil of the magnet or coil or loop if you want to call it that way. So the second one would be to increase the number of turns in the coil. Increase the number turns in the coil. And the third one, the third one would have been increase the strength of the magnetic field. Alright, so everybody okay with the three changes that you can make in order to get a bigger EMF? The increase the speed of the motion, increase the speed of motion of the magnetic coil, increase the number of turns in the coil, and increase the strength of the magnetic field. Good, nice. Right, so we're moving on again. Describe CXC students in particular. If you want me to run over anything, please let me know while I'm going through this. So I can work on it for you. The question here says describe what will happen if the magnet remains stationary in coil. We go back to our notes so you can see it was in the notes. So we go back to this one here. Not this one, this one. They said that how when you move the magnet in and out, there's a deflection in the galvanometer. There is no deflection when the magnet is at rest. So that means you are not going to get any voltage produced. So describe what will happen if the magnet remains stationary in the coil. There would be no deflection on the galvanometer, signaling that no induced EMF was produced. Good. So what it have to be moving, you have to remember that it have to be moving in order for you to produce a voltage. If it is not moving, the conductor or the magnet is not moving, you're not going to get any voltage at all. Good. So it must be moving. Instead of signaling, it should be indicating that no EMF was produced. Good. You all okay with that so far, CXC students? CXC. Nice. Moving on now. Figure 3 shows a simple layout of an AC generator. A coil PQRS is connected to other components of the circuit which allow the coil to rotate in the direction indicated by the arrow. Good? So, draw on figure 3 the direction of the induced current if the coil rotates in a clockwise direction. So, if we're using Fleming's, uh, which rule is an AC generator? So, which rule we're going to use? We're going to use Fleming's. Let me go back to the notes just in case you remember. So we're going to use generator. So we're doing generator first. Fleming's right hand rule is used for electric generator. So we're going to use the right hand rule. Then, so you, you put each finger as the thumb finger, the forefinger, the middle finger, and perpendicular to each other at 90 degrees to each other. Your direction of rotation is your thumb. So your thumb needs, let me put the thumb between S and P showing going upwards. Your 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 forefinger is pointing between north to south, your thumb points upward. So that means current will flow between P to S because the direction of S goes upward. Your magnetic field, I'm gonna draw it on the whiteboard here. Right. So this is between P, this is S, this is your magnetic field N, this is S here. So you're going to hold your fingers in this direction here. Your fingers are going to go so, and upward because why? Your rotation is clockwise. So this is your movement. This is your thumb. facing in that direction. This is your current flow, which is your forefinger. So this is your forefinger or current. This is current, and this is your and then here is a magnetic field. Then here is a magnetic field. Goes from north to south. So if you go to point in that direction, you would see that current goes between P to S. And then you would have the loop and it come back around. So that the next direction now, you're going to shoot the next side going downwards. Good? So your answer here, they're asking the question is said between draw on figure 3 the direction of the induced EMF. So you're going to put an arrow between here, showing the direction between P to S. Good? So you just draw an arrow going between P to S, pointing from P to S. Good? An arrowhead. Good, I can draw it in here on PDF. So good. We're moving on now. The period of rotation of the coil is 0.2 seconds. Calculate its frequency. Good, we would have calculated frequency. The formula for frequency. We're just going to clear this here. Frequency or period. Frequency F is equals to 1 over T. T being your period. So frequency is equals to 1 over T. So it's going to be 1 over 0.02 seconds. So when you work out that in a calculator, how much you get? 50. Good. And 1 divided by 0.2 is 50. So your answer is 50 hertz. And the only place that actually have 50 hertz supply 50 hertz is in China. They have 50 hertz, right? So they produce electricity at 50 hertz. Every other way in the world is 60 hertz. Then, so your answer is 50 hertz. So that's the calculation for this part of the passive question here. Calculate the frequency. What F is equals to 1 over T, 1 over 0.2 seconds. You get 50 hertz. They said if, as I said here in the question, if the speed and direction of rotation of the coil is constant, speed and direction is constant, sketch a graph of voltage versus time to show the output of the generator for one complete cycle, given that it starts rotating from its current position. So good, so you're going to have your voltage time. So that means your graph should look like this for one complete waveform, which should look like this, right? And you'll be in between here is 0.02 seconds. Okay, that's a complete waveform. That's the time taken to make one complete waveform. And the voltage that was produced, I don't know what was the voltage because it didn't say. Good, so everybody seeing the answer for this paper? Yeah, IGC students in particular. IGC CXC. You all okay with this? Good, nice. So now we're going to take a break and we'll come back here. Mm, half six because I want to start. Are you okay with a break now, or I want to go again and then? Because I know this generators question might be a little tedious and kind of brain wrecking for most people. We'll go from 6 to 6:15. We'll take a break from 6 to 6:15, right? 6 to 15 minutes break all I want or half an hour? Which better? Anybody? Any ideas? Alright, we'll take half an hour so we come back at 6:30. When we come back, we start on something called atomic structure and radioactivity. It's a kind of boring topic, but we need to get it done because it always comes. Good. So see you all at 6:30. Enjoy a break. Alright, good evening, students. I'm back again from our break. So we are going to do now something called atomic structure. Everyone here on the group chat. Everyone here? Good, nice. So good. So we're going to do something called atomic structure. Well, I have not posted. I didn't posted the thing. I'll post the lecture for you all. Yeah. So we're gonna. This is the last topic for the syllabus, which is radioactivity. Well, atomic structure, then radioactivity. So we'll be focusing on that for today and next week, and then we'll be doing some past paper questions, which to complete. Good. Remember next week Tuesday's class and Friday as usual. Um, this Friday's class as well. So we'll be working on the worksheets. Good. So these are the two lectures that we're gonna work on today. We might not finish them today, so reach how far we can reach, right? Good. So we're going to deal with atomic structure first and then radioactivity. And Friday, normal drift, we'll be doing the past paper questions, right? Calculation and past paper questions. So atomic structure. Atoms consist of three basic particles, which is protons, neutrons, and electrons. Um, so most of you all would have known about this way before. Um, when I did in the science, where your atomic structure in the center would have something called a nucleus, and then around it would have orbits, right? To which you would have the electrons. So here is the electrons. Good. And this is the nucleus. So this is your nucleus here. Nucleus. That's the center. And the nucleus consists of protons plus neutrons. And these are what you call the electrons. Good. Your electrons move around in orbits or shells. We call them orbits or shells or energy level. Each of these shells have different energy levels. Good. Um, and based on where these electrons are placed, will tell you the energy level of the electron itself. All right. Energy levels. Um, your so basically this is your atomic structure in simple terms. So we'll be dealing with each of these individually. Everybody see what the atomic structure looks like? Everybody okay with that so far? Nice. So we're moving on now to talking about each of these subatomic particles. These three basic particles, we call them subatomic particles, right? And these subatomic particles are proton, neutrons, and electrons. Your protons have a positive charge. This should be positive. This means positive here. Your neutron have no charge, and your electron have negative charge. They are different masses um, to keep the atom stable. Hence, since matter is made up of atoms, right? These atoms obviously going to have a mass because think about yourself. Yourself have a particular weight or mass, right? For us to have a weight of mass, we is made up of matter. We are made up of matter, and matter is made up of tiny particles called atoms, and atoms are further made up of proton, neutrons, and electrons. So each of these have a mass. Pay attention to that, and the mass will tell you the amount of overall full body. Good. So where the protons and neutrons are located, it is in the nucleus, as was shown in this in the picture here, and your electrons is on the orbital shell or around the nucleus. Good. Outside the nucleus or around. Okay? So we're moving on to something called nuclide notation. Nuclide notation simply tells you how the atom shows up in the periodic table. In any of the periodic table, you would have obviously something called your your atom or particle or something called your chemical symbol. All right, there are different chemical symbols because the periodic table is made up of different atoms or house different atoms. The chart itself you will need different symbols. So we call them chemical symbols, or in this scenario, they have them as X, which is atom or particle. The chemical or symbol represents the particular atom that exists in the world today because there are a number of different atoms that exist and they have charted it onto something called a periodic table. Right? The nuclide notation is basically a simple way that we can use to show elements. Good. So this is a periodic table here. I'm just gonna put it up on the screen for you to have an idea. So in your periodic table, I'm gonna show you here. Right. So everybody's seen the periodic table. They are different. I did this have some errors in it. I'm gonna just get the correct periodic table. Sorry. Um. Good. So this is a periodic table here of the different elements. Here. So these here you will see where it have by using a simple one, Si, silicon. Si is the chemical symbol, or we call it atom or particle. So it's the chemical symbol. Your atomic number is is the if you go back to the notes here, your atomic number is represented by this symbol here. Your atomic number is represented by Z, and A is your mass number. Your atomic number is the number of protons in the nucleus. Protons and neutrons are the same. Pay attention to that. The mass number, the nuclear number, is the number of protons and neutrons in the atom. Good. So let's go into the whiteboard for you to understand. So So this is silicon. So silicon is 14.7. Here is your top number is something called your mass number. We just go back to make sure. Your top number is your mass number. Your bottom number is your atomic number. So here is your mass number. Here is your atomic number. And here is a chemical symbol. Good. So your mass number is basically the number of protons. Everybody get this? I want to know if to clear this board and write again. Everybody get it so far? Nice. So good. So your mass number or the top number, we just say 14.7. That correct? 14.7. That's not even correct. Oh, yeah, 14.7, right? Good. For your 14.6 is only 14.6, right? Right? So for your so this gives you the number of protons plus neutrons, and this gives you the number of protons or electrons. Good. So if you want to find the number of neutrons, the number of neutrons, you can use your mass number minus your atomic number, right? Or the bottom number, top minus bottom. Or to find the number of neutrons, we could say is A minus Z. That's how we know it. Good. In the nuclear notation, if you go back to your notes, well, after you don't take down this, then we'll go back to the notes. My bad, 2814, sorry. Yeah. So silicon, sorry, it's 2814. Alright, so yeah, because I was just saying that something was wrong, right? Good. So silicon is 2814, sorry. So the number of neutrons is equal to the mass number minus the atomic number, where mass number is the top number and the atomic number is the bottom number. Good. So you want to minus the protons and neutrons minus the number of protons, so you'll get your neutrons alone. Good. And if you go back to our notes here, which is exactly what we're asking here, is the number of neutrons is equals to your mass number minus your atomic number. So that's how we're going to do it. For example, let me do carbon. Carbon is 12.6. I'm just going to do carbon as an example um, for you. Good. So carbon, everybody get this, right? So I'm just going to clear this. So carbon is 12, 6. C is for carbon, 12 is the atomic number. So you want to find the number of neutrons. So number of neutrons is equals to A minus Z. A is the top number, which is 12, minus the bottom number, which is Z, minus Z, which is 6. The answer is 6 neutrons. Good. So far we know that for carbon, your protons is 12, your electrons is 12. No, sorry, make a mistake. Your Your protons is 6 because that's the bottom number. Your electrons is 6. And your neutrons, how much we calculated to be? 6 as well. Good. So far, that's what we know. So to draw this, um, let's take off this portion here. To draw this here, this is your nucleus. So we're going to put 6p, 6 proton, 6n, 6 neutron. And outside that now is your first atom orbit, and the first orbit can hold only a maximum of 2. So you have 2 electrons here, 2. So 2 from 6 you would end up with 4. So you get 1, 2. Oh, I'll draw this a little bigger. 2. Remove that way. No. Good. Good. So we have 2, 3, 4, 5, 6. We have 6 electrons, which is 6e. That's this part here. Then we have 6 neutrons in the center, and then 6 protons in the center. Good, everybody understand how we get this? And then we have something called electronic configuration. Your electronic configuration is based on your your shell. In your first shell, how much you have? 2. In the second shell, how much you had? 4. So it's 2.4, right? Which means that in the first shell you have 2 electrons, in the second shell you had 4 electrons. Did everybody okay with that so far? Could we move on? Yes, nice. Good. So we're going to talk about something called isotopes. And then we'll go on to the next lecture. So isotopes, an isotope is an element that occupies the same place in the periodic table but has a different number of neutrons, which means that you can have one element but you can have 3 spots in it. For example, continuing, the number of protons and electrons are the same. An example is hydrogen. Hydrogen have 3 isotopes. We have something called protium, deuterium, and tritium or however I want to pronounce it. Again. Good. So one of them has 0 neutrons, the next one have 1 neutron, and the next one have 2 neutrons. So that means if we go back to the to hydrogen, I'm just going to show you. So for hydrogen, if we go to hydrogen here, hydrogen, your atomic number is 1 1, right? So that's the standard 1 1. So if you go back here, so we have protium, which is 0 neutrons. So clean here. So hydrogen isotopes, right? We have protium, which is 0 neutrons. We have deuterium, which is 1 neutron, and you have tritium, which is 2 neutrons. Good. So that means in hydrogen, we know that hydrogen is 1 1. So if you have one proton and you have 1 neutron, then if your atomic number, so if your mass number, because we learned it from just now, your mass number, um, so if your protons is 0, that means A minus Z going to give you 0. So in this scenario, 1 is always going to be atomic number, but it's going to be 1 minus 1 is 0 in this scenario here. For you to get 0 neutrons. So we go with A minus Z in the second one. A minus Z. What going to be your mass number here? If you want 1 neutron, your one going to all your mass number, your atomic number always going to be 1. So that means you're going to be 2. 2 minus 1 is 1 neutron. We go here. If you want 2 neutron, A minus Z again, you're going to be 3 minus 1, which is 2. So for protium, your chemical symbol going to be H, 1 1. Good. Then the second one going to be 2H1, and then the third one going to be 3H1. Good. So we get that. However, in the periodic table, it does have one block with hydrogen, but hydrogen have different isotopes. So that means it could exist as H21 as here, or H31 as here. Good. Everybody understand that? So the isotope means that they existing with the same atomic number, however, their mass number is different. Good. So there are different number of elements like that. The simplest one is hydrogen. There are many others. There are oxygen and so forth. But I just do the simplest one for you to understand what an isotope is. So everybody okay with isotopes so far? We are not going too much in detail because we do not have to do isotopes in general. So it's just understanding what an isotope is. So everybody okay with that so far? Everybody get that, or should I leave it on still? I want to take down that very well. I'll give you 2 minutes to take it down, or 3 minutes. Once you're done, take it down, then I'll go. Good. Let's just go over. I'm just gonna do our next one for you. I can remove this by the time. I can remove it, everybody. Okay, clear the whiteboard. Good, nice. So we're gonna do our next one for you to understand. So there's carbon isotopes. All right. So the carbon isotopes is you have C12, right, which is 12,6. Then you have C13, which is 13,6, and then 14, C14. Good. So C13 means that if you go to A minus Z, you're going to be 12 minus 6. You're going to have 6 neutrons. So one has 6 neutrons. The next one have A minus Z, which is 13 minus 6. You get 7 neutrons. And the third one is A minus Z again, which is 14 minus 6. You have 8 neutrons. So you have one with 6, one with 7, and one with 8. Now all of these are used for different purposes. C12, C13, C14. They are all for carbon dating, but for different aspects. All right. So that's another example of isotopes. They have the same atomic number but different mass number. Good. Atomic number. They have the same bottom number but different top number. Good. Which means that your neutron is going to be different number. Good. Everybody okay with that so far? Hmm? All right, too far is neat. And I call that look. There he is. Everybody agree is? Nice. Good. So we're moving on now. So we're moving on to here to chapter 50, which is radioactivity. We're going to talk about something called background radiation. Background radiation is naturally occurring radioactive decay of isotopes. Examples of sources of background radiation includes cosmic rays, earth minerals, and nuclear power plants, medical and dental X-rays. The most common we have is the X-rays, some cosmic rays as well, we notice, and the earth minerals. There are some earth minerals that we have available. Then, radiation, the random and spontaneous process of an unstable nucleus decaying. The process releases energy in the form of either a particle or wave, and sometimes both. Good experiments show that radioactive substances emit one or more of three types of radiation called alpha, beta, and gamma. These are all Greek symbols. Alpha symbols, alpha particles. We're going to deal with each of these individually. You would need to know, especially CXC and IGC, well, more so IGC, you would need to know how to do alpha and beta decaying, which is what we're going to do today. If we don't finish the calculations today, that's okay. Got Friday for that. Alright, so alpha particles, similar to helium, which is 482, it travels at 10% speed of light, very weak penetration power, stopped by paper skin and 6 centimeters of air. You need to learn these characteristics of each of these particles, all three, including gamma. But the decaying would be only for for alpha and beta. Strongly ionized, strongly ionizing because it can knock electrons out of atoms. Dangerous when inside body because it can cause exotic reactions to occur when with living cells and can cause mutations. Deflection of electric and magnetic field. So if you pass alpha particles between a positive and a negative field or in electric field, it would go towards the negative aspect of the electric field. However, if you place it between a north pole and a south pole or a magnetic field, it will attract directly to the, will make a 90 degrees deflection out of the, now this is out of the page, into the page, sorry. It would not go to, it look as if it go towards the S or out of the page, but it really means going into the page. So it come like it going between the two magnetic field, however, it go 90 degrees into the page. Here, for the the electric field, it is attracted to the negative plate. So you need to know this because in IGC, you need to draw it as well. Beta particles. Beta particles, high energy nuclear electrons formed when neutrons transmutes to proton. So you will add a set of voltage, you would have some voltages existing. So when you add it, you will get voltage. Travels at 50% speed of light, which is faster than alpha particles. Medium penetration absorbed by 3 millimeter aluminum. Weakly ionizing but dangerous because it is a free radical, strongly deflected by electric and magnetic fields. So in the electric field, the beta is strongly attracted to the positive. In alpha particles, it was attracted to the negative plate. Beta is strongly attracted to the positive plate, and in the north and south pole, it is deflected 90 degrees out of the page. But this one is out of the page, alpha was into the page. Alright, literally difference between them. Gamma rays. Gamma rays have high frequency, high energy electromagnetic waves. Travels at the speed of light, which is the fastest out of all of them. So it's gamma, then beta, then alpha. Right? Very strong penetration reduced by lead. Very weak ionization, but very dangerous. Damage cells and can cause mutation. Not deflected by electric or magnetic field, which means that it have a strong penetration. It could go through anything. Okay? What we use gamma rays for? Anybody have an idea what we use gamma rays for? Anybody have any idea what we use gamma rays for? We did this when we did the electromagnetic spectrum. Should I show a list? We did electromagnetic spectrum. Somewhere here. See it? So what we use gamma rays for? Scrolling down. Gamma rays, we use it. Oh wait, I didn't share a screen right. Yeah, this was notes given. We use gamma rays for medical tracers for killing cancerous cells and sterilization. Right, so we use that in chemotherapy, especially when it comes towards cancer. And thus gamma rays have the shortest wavelength, however the highest frequency. We did this when we did something called electromagnetic spectrum or electromagnetic radiation here. This is spectrum with all the wavelengths. Good. Right, so we're going with alpha decay. So we talk about them. So the strongest of them all, the highest frequency is gamma, then beta, and then alpha. However, go back for electric fields, alpha is attracted to the negative plate, for beta attracted to the positive plate. For alpha particles going through a north-south or magnetic field, it is deflected 90 degrees into the page. For beta, 90 degrees out of the page. Good. And gamma rays not affected by any electric or magnetic fields because our shortest wavelength is one of the strongest waves. Good. Alpha decay. An alpha particle is a helium nucleus having 2 neutrons and 2 protons. When an atom decays, its nucleon number decreases by 4 and its proton number increases by 2. For example, this is radium here. Shade here. You know what? I'll just show it right here. So here, the top number is known as your mass number. Your bottom number is known as your atomic number. So what they are saying is when you are doing alpha decay, you are going to always end up with a helium 42 because in alpha decay it releases a helium atom which has 4. 4 is your atomic number and your mass number is 2. So to make up 88, 2 minus 88, you're going to get 86 here. And 4 minus 226, you're going to get 222 here. Get it? So we get the Rn number. I'm going to share for the IGC. I'm just going to look for example. And I'll pass it by question one time. Very good. So we're going to do, I'm just going to show you an example here. So, so they said here, well, this is beta, I'm going to look for E. And we just um, let us do this. Yes. All right. So let me just go through the directory here and then I'll do an example. So far, so to get this here for the alpha decay, it is important to know that you're always going to end up with a helium atom which is 42, and you take the original atom, you minus 4 from it, so your top number is going to be 222, and 88 minus 2, which is your bottom number, you're going to get 86. That's how you do alpha decay, right? For beta now it's slightly different. In beta decay, a neutron changes to a proton and an electron. Here, right, the proton remains in the nucleus and the electron is emitted as a beta particle. The new nucleus has the same nuclear number, but its proton number is increased by 1. Important thing to note. So when I'm doing this, so we go with 14,6, right? Carbon 14,6. So Your top number remains the same because you're going to end up with an electron at the end. However, for you to get 7 here, because you have a dating of a carbon atom of 14,6, if your nitrogen atom is 14,7, 1 electron, your the number is -1, which means that you would get 6 here. So basically, this number going to be 1. You need to add 1 to the bottom number, right? Which is the proton number. You're going to increase by 1 here. Your top number remains the same, however, your bottom number increases by 1. Because if you go to -7 minus 1 is 6, which remains the original value. Good. Um, Positrons or B plus beta plus can also be emitted in beta decay. They are subatomic particles with the same mass as an electron but an opposite positive charge. Gamma emissions. Gamma emission after alpha and beta emission, alpha or beta emission, some nuclei are left in an excited state. Rearrangement of the protons and neutrons occur and a burst of gamma rays is released. Right? The gamellar tube, um, the gamellar tube, when an alpha, beta, and gamma radiation enters the tube, it produces ions in the gas. The ions created in the gas enable the tube to conduct a current, produce a voltage pulse, and each voltage pulse corresponds to an ionizing radiation entering the GM tube. The voltage pulse is amplified and counted. That's how we do testing on radiation. Um, you'll get into more details when we're doing past paper questions to have an idea. We have something called half-life for life in radiation. So as elements start to decay after time, when anybody or any object dies, and then when it now starts to die, the it started decay rapidly and then it starts to slow down after that. And the same thing with any isotopes or any element that undergoes radiation, which means that at the early stages of its life, there's rapid decay and then gradually it starts to slow down. Okay. Half-life. Half-life is a measure of the time it will take for half of the source to decay. Then the quantity of the substance is equal to the original amount multiplied by half raised to the power of the number of half-life. All right. I'll explain this in detail next week. Not next week, Friday. Sorry. When we're doing passive questions, because that's the only how you understand. Example: the half-life of this graph is 2 days. So you started with 4 and then 2 here. So use of radioactivity. What we use radioactivity for? First thing is carbon dating. That's what we use C14 for. Carbon dating. It determines when an organism dies based on the carbon 14 level within their body or bone structure. Carbon 14 is the carbon content in your body. So based on that, they will tell you exactly when the organism died. The second one is treating cancer. We use gamma rays for that. Radiotherapy localizes the exposure of activity to the area of the cancer growth. Chemotherapy is a whole body exposure to radioactivity. Whereas radioactivity, there's a difference. Radioactivity is only for a particular area of the body. Chemotherapy is for the whole body. However, they use gamma rays to kill these cancer cells faster than killing the healthy cells. That's what's going on with the gamma rays. However, if being exposed to too much of gamma rays, the healthy living cells tends to mutate. So we try to do that. So that's why they only expose it a certain amount, especially if you have cancer. If you're doing radiotherapy, they only allow you for a certain time, or maybe just say about 10 sessions or 12 sessions till the thing beyond that. could cause cell mutations. Then medical traces. We use it for medical traces. Good. Radioactive source substance inject into the body and migrate to the area doctors are investigating via the use of detectors. So they inject some radioactive substance is going to localize or stick around the region in the body, and the doctors will use detectors, form a detector that will identify the area. Good. Next thing is thickness gauge. That's what we use in finding faults in pipelines, especially when you weld it. We use our X-ray vision that actually detect the flaws, sorry, or the cracks along lines um in any material. They call it non-destructive testing. Yeah. Um. So they use X-rays and stuff like that. Sterilization. Gamma rays used to sterilize medical instruments. Not sure if all you ever noticed this, but some medical offices, especially dental care, they have a little oven that they would put in the components in, and they would put it on like a microwave, and it would heat it. Those gamma rays are emitted to sterilize the components before they put it into your mouth. All right, that's the next way they use it. The dangers of radioactive materials. Socially, one, it can cause genetic mutations in your cells. And that's what radioactive materials do. Uh, Also, it can cause sickness of people and animal. Anybody ever hear about the Chernobyl disaster before? I think they had made a movie on it though. The Chernobyl disaster. Yeah, it's based on the same gene mutation and so forth. Um, it was well, like read up on it or watch the article on it or movie or the video. Alright, it's a real nice thing to know. Good. It cause sickness to people, which cause a good bit of people to die. Um, Also, the dangers of radioactive materials based on environments, it could cause crop mutation and pollution of atmosphere, land, and sea. Um, when they say crop mutation, is that it could cause the crop to either yield good. However, even if it yield good, remember once the crops are mutate, that means our body wouldn't get accustomed to the structure of the complex crops or whatever it be. So will be affected on the long run. And economically, high cost to store radioactive materials. That's one of the drawbacks because you need to have confined containment for any radioactive material. Um, Second one, high cost to quarantine area should should radioactive materials be leaked. Good. And the reduction to tourism. Good. The high cost of quarantine you can see, especially in this time that we're going on with this quarantine period. The quarantine alone going to cost us a lot of money just to quarantine, especially if it have radioactive materials, and that will reduce tourism because nobody will want to come in the country. Same thing with the Chernobyl disaster. When it had happened, the quarantine was it took a long time. Besides, it took a lot of money, and tourism was at a real low because of the fact that nobody wants to go to where that happened. Um, to avoid getting contaminated and so forth. Good, you need to learn this. Everybody need to learn the dangers of radioactive materials. Um, I'll do one, two examples of pacifers. Just in a minute, let me just um, let me just Right, good. So sorry about that. Right. So we're going to do how does do 1 2 questions with in IGC. So you have an idea how we do the past papers on this. Mind you, whoever doing IGC, you do these questions, this topic in particular, do not come in your paper 61. Okay. So you're only going to get this in your paper 21, which is your multiple choice and instructed paper. Mm, Right. And before we do that part, we'll do this part here. Right. So hydrogen 3 or tritium, good, has 1 proton and 2 neutrons. Good. So that means your mass number going to be how much here? If it have 1 proton and 2 neutrons, 1 plus 2 is how much? Hmm? We go through it for the IGC people. The question is hydrogen 3, which is tritium. We did this as an example, has 1 proton and 2 neutrons. The nucleon number of tritium is 3. It decays by beta, so that means the top number going to be 3. Good. Your bottom number for hydrogen is how much? How many protons it have? 1. So bottom number is 1. Good. Beta, what we say about beta particles? Beta particles going to always give you a 0 and a minus 1. Good. Beta or electrons. So I'm going back to the notes for you to see. For your beta particle, what's your beta decay? Well, beta is the same thing as E is an electron, right? So beta is 0 minus 1. So whatever you're going to do, this number must be bigger in order to give you the result. So if beta is 0 minus 1, how much you think the top number here going to be? What going to give you? What plus 0 going to give you 3? It's going to be 3. So x going to be 3. And your bottom number for x. What minus this going to give you 1? You're going to get 2. So we get 2 minus 1 going to give you 1 here. Let's see if I can highlight that. Alright, so 2x 3 2. So 2 minus 1 going to give you 1, and 3 plus 0 is 3. Everybody see how we get that? For beta decaying. As you see, students, this is the hardest this will come. Just add some small numbers 4, 2, 3, and 1. All understand how we get it so far? That's the 3 marks. Nice. So we're going on again. That's that. I'm gonna do our next question for it. So we're gonna do this. We're gonna do some more questions. I'll just show you now. Let's so like have an idea. Right. Here's another question for IGC students. Here are the questions. The isotope, radioactive isotope carbon 14, which is 1460, emits beta particles as it decay. The Decay of carbon-14 produces an isotope of nitrogen. State the nature of a beta particle and state where it is produced. We will do that next time. I only wanted to understand this part of the equation. Complete the nuclide equation for the radioactive decay of carbon-14. So we know beta is what? You have to have 0 and 1. So you put in 0 here. First thing as you see, take a 0 and -1 because you know beta is -1. Good. So, right. What plus 0 going to give what plus 0 going to give you 14? You're going to get 14 again. So 14 plus 0 going to give you 14. And your bottom number should be what? What should be your bottom number? 7. Good. Because 7 minus 1, you're going to get 6, which is exactly what we want at the start here, at this point here, 14.6. Good. Also, nitrogen is 14.7. So, um, as that we will do the other questions like these these theory questions, we will do that later on. I just wait to understand this part here. I'm gonna do our next question, making sure you understand. Oh God, this gets really. I'm gonna see if I get next question. Right, good. Share this one. Boom. Let me see if we could work on this here and see thing. So radon 222 is radioactive. It can be represented as 22286 radon, which is Rn. For a neutral atom of radon 222, state the number of protons. How many protons do you think it have in this atom? You remember the top number is the number of protons and neutrons. Your bottom number is the number of protons or electrons. So how many protons it have? 86, good. So it have 86 protons. It have 86 protons, good. How many neutrons it have? How we calculate neutrons? You're calculating the top number minus the bottom number to give you the number of neutrons. So you're going to be 222 minus 86. How much I get? Which is the top number, 222 minus 86, which is how much we get? No, work it. 136. Good. 136. All right. How much is the number of electrons? The number of electrons is the same thing as the number of protons, which is 86 as well. Good. So everybody understand how we get that? Nice. Right. We're gonna complete this now. This equation. They said radon 222 decay by alpha emission to polonium nucleus. Complete the equation of the decay. Now is by beta. Sorry, not beta, alpha here. So if it is polo is PO. All right, I'm gonna just write it back. I'll write it in a whiteboard for you. Um, so clear. Oh, all right. So we have 2, 2, 2, which is radon over 86. It is alpha decay, which means that in alpha decay, your alpha decay going to be 4, 2, because it is the same thing as a helium plus um, polonium. But remember, let me go back to the notes for you to see. Share, let me go back to the notes. So in alpha decay, its nucleon number decreases by 4 and its proton number by 2. So everything, the top number decreases by 4 and the bottom number decreases by 2. So we go back to the whiteboard. So 86 minus 2 is how much? 84. So that's your bottom number. Your top number, 222 minus 4 is how much? 222 minus 4 is 218. So your top number is 218. Nice. So everybody see how we do that? Especially IGC students. So that's what equation going to look like. If you do have alpha, you can also use this here. You can also write HE if you want. Or if not, some participles, like for example, in CXC, we don't put HE, we put alpha. You could use alpha, it means the same thing. Again, which means this is alpha decaying, which is 4,2. So everybody understand how we do alpha decaying and beta decaying? Because that's the only two decays you need to do. CXC is the same thing. That's the only two you need to know. You don't need to know gamma or anything. The others you would need to know is how to calculate half-life and so forth. We'll focus on that a little more next week. So are you okay with this so far? IGC students and CXC students. I only see one person replying. Right, nice. So do one more question and then we should wrap up for that after. I just want to make sure you understand how to do this decaying because next week, I'm not next week, Friday when we do the others, the half-life calculation. I don't want it to get mixed up with this now. So see if I get some more possible questions. Right. Like any question here says in number 11A, the 2018 paper, IGC, and they said figure 11.1 shows the data of 9 elements: helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Carbon 14 is a radioisotope with a nuclear number of 14. It decays by emitting beta particles. So beta is 0 minus 1. Right, minus 1 and you know. Use any data you need from figure 1.1 to write down the nuclear equation for this decay. So we talk about carbon 14. Carbon is what your bottom number is 6. So let me go to the shared screen. The whiteboard, sorry. Clear? So we're going to use carbon. So it's 14, carbon 14 data. So it's 14, 6, and it goes to a beta, a beta decay. So it's 0 minus 1. So you're going to break up into something. Um, so what going to give us 6? Minus something minus 1 going to give us 6. It's going to be 7. All right. So we go back to our table now. Go back to the table and see which element is that. Which one has 7? Nitrogen. Good. So nitrogen is 7. So we're going to use nitrogen element here, which is N for nitrogen. What plus 14 going to give you? Um, what plus 14? You want 14 here. What plus 0 going to give you 14? The answer should be 14 here. Good. So here going to be 14. So when carbon 14 goes through a beta decay, you would end up with nitrogen 14,7. 14 plus 0 is 14. 7 minus 1 is 6. So we get, so yeah, that's all we need to know. What is beta and what's alpha? Um, alpha is 4, 2. Good. Always remember. So these are the only two things you need to learn if you're doing these decay equations. That's the only two things you know, both CXC and IGC, because you're not doing any gamma. So pay attention to that. So just learn these two by heart, how to do them. Good. This is beta and alpha decay. Good. This is beta here. Um, Beta. This is alpha. Good. So take down that. Once we get to that, Friday we gonna do. I'll compile two worksheets. One with CXC and one with IGC. I'm going through that, and then we will we finish out that Friday, right? And we'll move forward after that. We'll discuss with the plans and what after. Right. Any questions concerning today's class? Any question, anybody? No. Everybody else good because I only seen just a very few of them um replying. Bon, very few, literally few. Had a good bit of students over, but they just elope. Good. Right. So Friday we'll be on here from 5 to 8. We do participate questions on radioactivity. Um, we'll be doing more half-life calculation and things. So just pay attention. Just go through the notes, learn the definitions because the definitions important, and we'll work on the calculations for that. Any other questions that I'm giving you problem, you bring it to my attention, so we'll go through it. Another thing to note is that whoever doing exam this year for IGC, all IGC exams are put off, so you could be able to write the exam in November. Hopefully, this Corona epidemic, not epidemic, pandemic, is over, and CXC students, if you're a private student, you only are allowed to write multiple choice question on paper 3, which is your lab paper. Or if you have already done your SBAs, you're only allowed to write your multiple choice to get a grade. Good. For multiple choice for CXC, I have some, so I'll work on them from next week. Hopefully, we finish out this topic here this Friday. Next week, we'll do some more multiple choice on that. I'll forward it on the group chat. So you could get access to the multiple choice. We could work them together, or you could work them, and I could follow up for the IGC students who have already signed up for exam. Well, I guess they would make the arrangements for you to do your exam another time. If it is be in November, then you have enough time to study. However, we'll still continue doing past papers as usual. Good. Any questions? I hope everybody's safe and trying to be safe at least. Good. Any questions for today's class? I want to just explain about the exams for this year. Any questions? All good, good, nice. So these lectures have already been posted to you, so on WhatsApp, so you could go through it. I'll post the worksheets for you on Friday or probably before. Kind of caught up in something else. So after today, class we'll be focusing on doing the past papers for these, and next week cover up on whatever topics and multiple choice questions. Good. So see you on Friday around 5 to 8. We'll be doing past paper questions, like if you could actually sit in, because that's the most important class, how to do the calculations and things, especially if you're doing this, because all questions, all paper two must have a radioactivity question. All right. Well, you're not gonna paper two for CXC, but you must do it for multiple choice in paper one. All right. So everybody enjoy the night and be safe. Remember to keep safe and do all precautionary measures so that you don't get sick from this corona pandemic. All right. Good night and be safe. Mhm.